I liked the idea of putting an outline on the board, but doing it intimidated me no end. I looked at that and said, wow, we're really going to do all that? I hope so. Pierre Louis encouraged me that it's possible to have a big outline and get through it. But I want to start with a correction and thank the group of you who asked me some good questions about what I thought was a Gödel incompleteness theorem. And I told you on the first night that I hadn't written it up or anything, and I retract it, but it's a design issue. I think we could make some kind of Gödel incompleteness theorem out of it, but I'm not going to do that. So I fixed the slides because I can't. I mean, I can't yet. But there's only one slide there that we have to that I retracted. So I put the new talk up, and I just took the Gödel result out, and I'll tell you maybe a better story, a more open-ended story. And I liked Pierre Louis' comment about it. He said, well, you got a really good story in there and just have to find out what the conclusion is. So here's a conclusion, which is actually more stunning than, I don't like it quite as well, but it's sort of stunning what's happening here. So instead of talking about Gödel's theorem, what we see is I wanted to have this factoring. So we could say Scott arithmetic is going to be a constructive Scott arithmetic plus P or not P. And I thought that we were going to get the Gödel theorem because over here on this side, when we seem to have a very simple formula, we're going to say for all n bar here, either you converge or you don't converge. And I thought, I assumed when we actually filled out this theory and said exactly what Scott arithmetic was, there'd be some condition on this. We wouldn't be able to just do it straight out. But you certainly want to. As a design principle, I guess we really should say you better be able to do that or the contrast isn't so good. But what we now notice is pretty stunning. If you put P or not P into this theory, what happens? It becomes inconsistent because we had this result that in the constructive theory, in CSA, we actually can prove, if we call this thing the convergence theorem, as I did in the notes, we can actually prove, let's write it like this, not the case that CVT. So that's just not going to be true. And so when you put P or not P in here, you're going to get CVT. So what we notice is instead of factoring, when you put this thing in, this theory becomes inconsistent. So instead of factoring, what we do is we separated these things. These guys, P or not P, cannot live with the constructive Scott arithmetic that we sketched. And that's the kind of theorem I was trying to avoid. It's what got Brouwer into trouble when he would state things like, all the functions from the reals to the reals are uniformly continuous. People would say, oh, that's wrong. And maybe that's how you're going to react here. You say, well, okay, you put P or not P in here and you're going to get a contradictory theory. So this guy, this Scott arithmetic, a constructive Scott arithmetic, must be flawed some way or other. But I don't actually see the flaws in it. It looks pretty good. And for one thing, you get a really nice proof of unsolvability. You get a limiting theorem in here that's really pretty elegant, right? We got the halting problem. We got the negation of this, which is the halting problem without having to Gödel, use Gödel numbering without indexing the partial functions. So that's something that I think is pretty cool. We didn't have to introduce some kind of Church's thesis and index the recursive functions. So this is a form of unsolvability without Church's thesis. So here we've got it. We know not this, so not this theorem. So we have unsolvability without Church's thesis. So that's what I should have started with. But I would guess that I wouldn't give up entirely. When I'm on the airplane, I'm going to be thinking, what is the restriction I believed we should put on the Scott arithmetic so that we could get some kind of real incompleteness theorem? But I don't know what it is at the moment. Okay, does anybody have questions, comments about that? So it's not Gödel's theorem, but it's undecidability without Church's thesis, without indexing, and so forth. Questions? No more? So if you've got good questions, by all means come up after, because I started to explain to one of you about why I couldn't use P or not P, and the explanation just, I thought, wow, that's not going to make sense. I don't know what the restriction is that I wanted to put on. So anyway, come by all means, ask questions. Okay, so that takes care of this. Now, here, the only reason I wanted to do a little bit more of intuitionistic first-order logic is so that I could show you what Poincaré and Brouwer saw. So this isn't very deep, the stuff we've been doing. You're really familiar with it, so I won't take much time at all. I think maybe I won't even bother to show you this, another extract or the rules or anything. But let's, unless you want, I mean, I could do one. I've got one written in the notes, but I'm thinking it's probably better to get on to the deeper stuff. By the way, another little comment here, which you can see very clearly from the lectures of Pierre-Louis and Hugo, is that we've got much more sophisticated embedding technology. When we talk about relating a classical theory to a constructive theory, we can now do that in a much more computationally interesting and sophisticated way. So I should have known before, I should have realized this is not a good thing for me to talk about, because those embeddings are all much more powerful now than what we had, or what Gödel had in the 40s. Okay, but let's look at intuitionistic first-order logic. We see what some of the extracts are, and we know that, for example, when we're writing down an implication, A implies B, we're going to start the proof out by saying, assume you've got something of type A. So you're going to start off like this and try to prove B. So you're going to get functions. When you're trying to use a function that's in the hypothesis, A implies B, you've got some other hypotheses you're trying to prove G, we know that you're going to be applying that function to some argument A. So those are two of the constructors we're going to have. But for every one of the, so here we're doing it for implication, we know that for and, we're going to use pairs, and we're going to have a spread term. When we do or, we're going to have in right and, let's put it on the right, in left and in right. We're going to have a decide term. When we do for all, we have the same thing exactly. We're going to have a lambda, we're going to have an application, and when we do existential, we have the and. So basically, these are the realizers that we have available when we're doing first-order logic. Now, basically what the Principia guys were trying to do was reduce mathematics to pure logic. And if you think of trying to do that, say, for number theory, you say, okay, let's look at arithmetic and see what would happen if we wrote down induction in the first order logic that we have here, and we just axiomatized that way with an induction scheme. So we could write down this first order formula, assuming that our domain consists of the natural numbers. We could write induction like this. So we'll say, all right, we have this induction principle. If you know P of 0, and if, say, for all n, and we're assuming natural numbers there, so say for all n you have P of n implies P of successor of n, then from this we should be able to conclude for all x, P of x. Now, I would rather do this induction without actually introducing any function constants, and we could certainly do that. We could write this by having a predicate, say 0 of x, and that predicate would be true just for, well, we could, and we could also, if we wanted, axiomatize an equality relation, but not build it in as primitive. But let's say all we did right now is we had a 0 here, and then we had a successor relationship. So y is the successor of x. We could rewrite this without that function symbol. Now, I ask you to think about what kind of, so we write this down as a first order axiom. We just add it to the rules that we have for intuitionistic first order logic. So we take IFOL plus this induction form, and we say that's arithmetic. Say that's Heiting arithmetic. And we start to happily do our proofs about numbers. We prove that there are infinitely many primes, and we go along having a good time. So what do you notice anything that's going to be very disappointing about this approach if we try to do, say, proofs as programs or extraction, something like that? So this is essentially, if you were listening to a lecture from the logicists, they'd be proposing something like this. Here's how we get to number theory. We just take this first order formula and we add it as an axiom schema parameterized by P. So what's wrong with that? What's missing? What did Poincaré see? What did Brouwer see when they were told, this is the way we're going to do math? It's all pure logic with some assumptions. So here's one, induction. What's wrong with that? So you all actually, I'm sure some of you know what's wrong with this. Suppose I'm trying to compute here. I now want to build a function by induction. I want to build a factorial, or I want to decide primality or something like that. Is this thing going to do me any good? So the only way you can compute with this is you'll have 0. You can establish P at 0. And to establish P at any other number, you're going to take this induction hypothesis and use it over and over any number of times you want. But how are you going to get the lambda here? How are you going to get this? You won't be able to get it. You won't have an induction form. So what do? What does Koch do? What does Newperl do? And this is what Hugo was talking about in one of his early lectures. He was saying, look, if you're just using system F and you're trying to do induction, you're kind of in a situation like this, where you don't have computational forms. You don't have induction forms. So we have to actually supply the realizer. And what you do is you build a term. In our case, we have a term called ind has this component n, and then base, and then two variables here, say u and I, and then some body f. So we have a term like this, and we tell you how to compute with it. So what we say is, okay, if this end form has a 0 in it, then the way it's going to compute is it's going to reduce to b. But if the end form starts with some successor, like n prime, say, then it's going to take this function f, and it'll reduce to f with, say, n substituted for u, and this whole induction form on n now substituted for I. So you need those evaluation rules on a new computational primitive here. And you get this when you're doing recursive types. Again, as Hugo pointed out, if you just take Mendler's definition of the recursive types, he provides these combinators, these realizers for all the inductive types you can build. So it's not good enough to just be in intuitionistic first-order logic if you want to do anything, right? If you really want to compute stuff. So do people see that? That's why we have the recursors and the induction forms. So when you think of a principle you want to write down, the principle better be something that you can write a realizer for. Okay, otherwise you've got a very weak form of constructive logic. All right, so that's what Poincaré saw, and Brouwer too, and they talked about it. There's a lot of literature on this as they went back and forth, and I think from this point of view you can read it. You can say Poincaré and Brouwer realized you needed this, and everybody was acting as if all you needed was that. And they were trying to do induction and cheating all the time to get there. Okay, so now let's show something that's probably new. I would imagine you all haven't seen too much of this kind of logic. I mean, there are people who are working with uniform quantifiers, but not, as far as I know, not doing induction with them. So I want to talk about another operator now. So we know what for all x of type B something P of x is, of type A, say. We all understand what we're talking about there with that quantifier and how to prove things. But I want to introduce a quantifier that we're going to write like this, but this is going to be the display form for it, and we're going to call it a uniform for all. But the actual type that we're using here is an intersection type. So what I want to do is intersect over the x's in A, this is my index set, all of the values that could occur here in, say, the proposition. This could be any type, but I want to think of it as a proposition. So let's find one interesting example where this turns out to be different from what you get with this quantifier. Suppose I want to write down a formula like this. For every proposition P, for us we have to index those propositions, index of I. We want to say P implies P. Okay, so what does the extract look like for this thing? It's going to say lambda P dot lambda x, say x. Here is a realizer that belongs to that type, right? It's a lambda term that takes a proposition and returns evidence, returns the extract of a proof of P implies P. But notice that we don't use the P in here anywhere, because in our polymorphic logic, we don't need it. If we had insisted on types, then this would be necessary. So if we were looking at a term that was like this, for all x of type p dot x, then of course p actually occurs here, and you need this outer quantifier. But I mentioned in the beginning that our whole logic is polymorphic, and that sets it apart from a Coq-like logic, where the terms, where variables are explicitly typed. Here, this thing is implicitly typed, this x. It's implicitly typed to be of type p.
You can think of it as a query style. Is that basically?
Yeah. Yep. That's what this is. But here, we're going to go a little beyond that, and we're not, we're actually going to do this uniformly. So here, you're seeing the Curry style thing. But now I'm proposing that over here, like, let's take the intersection now. If we do this intersection P in prop of P implies P, then you get only, in fact, the only thing in that type is essentially lambda x dot x, right? So you get this in there. And we're going to do it for not only lambda terms, a la Curry, but we're going to do this over the numbers and everything else. Okay, so so it's reasonably clear where we are so far? Okay, so now let's write down a polymorphic induction principle. Let's see how to make sense of that. And I don't think this stuff is real easy. You could reconstruct it in your head in just a second. So let's write down, say, complete induction instead of the simple standard induction I just gave you. Let's first write down the standard form of complete induction. So we'll say, and I'll use this kind of notation. I'll say n sub m here is the collection of all x's in n such that x is less than m. And let's say we write complete induction this way. So we'll say, let's see, so for all n in m, if we know that for all x, say, in m sub n, or if we assume p of x for all those x's, and we can prove p of n, then I keep alternating between arrows and this. Then we know for all n and n p of n. Okay, so that's ordinary complete induction, where the base case here, we don't have a base case because when n is equal to 0, you've got this empty type and you plug in the identity function and you can get going. So I assume you could all write down a realizer for this. It's not trivial, but you could do that. But now I want to show you a different kind of realizer. What happens if we switch the quantifiers here to be these things? So I'll say for every n in n, and over here I'm going to also do for every x in n sub n. And then at the outside, out here too, we'll have for all n in n, p of n. So does this make sense, first of all? So what we're looking at here, when we conclude that we're going to have something in p of n, we're not going to be able to use this n, right? It's just an index. And likewise here, these intersection types aren't actually letting us get a hold of the numbers. So this is a very uniform kind of induction principle, and we'll prove it in just a minute to convince you that it's a true and meaningful induction principle. By the way, classically, these two things are the same, because classically, you think of this as a truth value, right? That's just true or false. And so over here, you say, well, yeah, this is fine, because I just either have true in these types or false. Okay, so let's see if we can make sense of this principle by proving it. And question is, what's going to come out as, once we prove it, we'll be able to get an extract, right? We will know what the computational form is for this, and it should be amusing, right, to see what is that. So let me give myself a little more room for this proof. Well, maybe not. Maybe I don't need any. I'll just make the quantifiers. I'll give myself a little more room by reminding us now that we're going to do these uniform quantifiers here. So all the quantifiers are uniform. Okay, so we're trying to prove this. And first step is easy. So we're going to get a hypothesis over here, H, that we have for all n in n. We've got all this stuff here for all x's in n sub n. We assume p of x. And we get p of n. So I better get the parentheses like that. And we're supposed to show here this. Okay, and now we can take one more step. Let's combine the two steps. So here we're just going to introduce the quantifier again. So we'll make this another hypothesis of this form. So we've got an n of type n, and we're supposed to show p of n. Okay, now, yep.
And the left of H has the non-uniform.
I'm sorry, nothing should be non-uniform. So that's uniform. It's all uniform. Okay, so what are we going to do? We've got, so here's a first thing to notice that I didn't tell you, but it's, we have a paper on this that I posted on the web. It'll be there. If it's not there now, you can look, maybe it's there. We call, Mark Bickford and I have this little document called Polymorphic Logic, and everything I say here is in that document, so you won't have to take really careful notes. Okay, so in the normal use of these intersection types, you have to hide hypotheses like this, because so not only does this mean it's uniform, but in the new Perl logic, when I write a hypothesis with these brackets around them, it means I can't use this guy in the computational content over here, because I don't actually have that particular n. However, we'll see in a minute that if the goal doesn't have computational content, then I can unhide all those hypotheses. So I want to draw your attention to the fact that at the moment, these hypotheses here, this is called a hidden hypothesis. And if you're doing a general proof with these intersection types, we actually put that square bracket around to say the thing is hidden. Okay, so now let me just make sure I don't go down the wrong path. Oh boy, do these notes look. What we wrote up looks a whole lot nicer than this. Okay, so yes, so now comes the stroke of insight here. The way we're going to prove this is we're actually going to put the fixed point combinator of, and I see in my notes I called this F, so let's call it F so I don't get totally screwed up here. We're actually going to decide what we want here as the extract. We're going to say we want to put in this type the fixed point of this guy. And that's not too unreasonable. If you thought for a little bit about what the actual recursor, realizer is like for complete induction, what does it do? It basically starts off with the identity function in the base case, and it just iterates this function f. So if that's what's happening in the normal proof, it's an interesting idea to see if we could actually put the fixed point operator in here. So we're going to change the goal here now and say, I want to show that fix of this f is in P of n. Now that's just a typing goal, right? We're just trying to show that this guy, fix of that f over there, is of the right type. So this thing doesn't have any computational content. We've gotten into a position where we're just trying to show typing. We're doing type inference here, which, by the way, is how NuPerl does all of its typed reasoning. We don't have decidable types there because of our extensional equality. So for us, in order to show something is in a type, we have to do a proof. But we've carefully automated that, and most of the time, the theorem prover gets the typing, but it's not going to get this right away. So once we're in a non-computational setting here, where we're not trying to build computational content, we can actually unhide these guys and get access to the function f and the n. Okay, so all of these things can be unhidden now that we've changed the goal to this. Okay, so how are we going to actually prove that? So what we have here, if you look at the typing of this, you can see that if we apply fix to it, we're going to have that fix of this f. Let me check this. This thing can sometimes get me, yeah. So fix of the f is going to belong to this intersection type here. So to this for all x in n, well, now I can leave those braces out. P of x implies P of n.